A very good morning to all of you. Today I am giving a lecture on analog communication. These are the three waveforms in which the first waveform shows the modulating signal, the second waveform shows the carrier signal, and third waveform shows the amplitude modulated signal. In amplitude modulation, the amplitude of the carrier varies in accordance with the instantaneous value of modulating signal or message signal. The first waveform shows the message signal. This one, and the second waveform, the carrier signal. This, the amplitude, as we have seen, we have noticed that the amplitude of the carrier varies in accordance with the modulating signal or message signal. So this is the amplitude modulated wave in time domain representation. Now we analyze this amplitude modulated wave mathematically. As we know, the equation for message signal is given by Em of t is equal to Am cos 2 pi fmt, and for the carrier signal Ec of t is equal to Ac cos 2 pi fct. Here in this modulating signal or message signal, Am is the amplitude of the message signal and Fm is the message signal frequency. Similarly for carrier signal, AC is the carrier amplitude and Fc is the carrier frequency. Now the amplitude modulated signal is given by E of t is equal to Ai cos 2 pi fct. So the from the definition of this amplitude modulated wave, we are adding our message signal in the amplitude of the carrier. So AC plus Em of t into cos 2 pi fct. One plus k into Am cos 2 pi fmt and upon AC into cos 2 pi fct. Here this k is the sensitivity constant, which is assumed to be value is equal to 1, and this Kam upon AC is the modulation index in case of amplitude modulated wave. So AC into 1 plus Ma into cos 2 pi fmt into cos 2 pi FCT. After simplification, we are getting this carrier frequency component AC cos 2 pi FCT plus MA AC by 2 into cos 2 pi FC minus FMT plus MA AC by 2 cos 2 pi FC plus FMT. So this is the carrier frequency component, and this one is the lower sideband due to the presence of this FC minus FM, lower sideband LSB, and this one is the upper sideband. And so we got this three frequency component after simplification, this equation of amplitude modulated wave. Now this analysis is shown in this time domain representation. We want to analyze our the amplitude modulated wave in frequency domain also. So there are when we take the Fourier transform of this equation, we convert this amplitude modulated wave from time domain to frequency domain. So after taking the Fourier transform of given equation, then we get this E of F E of F is equal to, now before going to take this Fourier transform, what is the we know that the Fourier transform of this xt cos 2 pi FCT is 1 by 2 capital X F minus FC plus capital X F plus FC. Now the Fourier transform of this xt cos 2 pi FCT is equal to 1 by 2 into capital X F minus FC plus capital X F plus FC. So the Fourier transform of this equation, the first component is AC cos 2 pi FCT. Similarly, we can AC by 2 is equal to del of F minus FC plus del of F plus FC. Similarly, for lower sideband MAC by 4 del of F minus FC minus FM plus del of F plus FC minus FM. And for this third component, the MAC by 4 into del of F minus FC plus FM upper sideband, and similarly del F plus FC plus FM. So this is the, after taking the Fourier transform, we are getting this equation in frequency domain. Now we draw the x-axis is for frequency, and the magnitude of this capital E of F is shown here at y-axis. So the magnitude, we have three frequency component. The first one is the carrier, and second one is the upper sideband and lower FC minus FM, and similarly with negative sign. So the magnitude of this frequency component is AC by 2, and for lower sideband magnitude is MAC by 4. So this is the spectrum of amplitude modulated wave in frequency domain after taking the Fourier transform. Thank you.